Hi class! Today we're going to start into finding derivatives, differentiation, using the limits of difference quotients. And we have two objectives today. We want to find derivatives and values of derivatives, and then we're going to use those derivatives to help us find the equations of tangent lines. So let's get started. In the last section, we talked about the average rate of change. The average rate of change is equivalent to finding the slope of the secant line. This is the secant line that I drew here in blue. It's a line that goes through 2 points. The x value of these 2 points is x and x plus h. And so we find the slope by using that the difference quotient. And when we did that, we found the average rate of change. Now we're talking in this section about something different. This section talks about instantaneous rate of change, and that is if instead of having 2 different points, we say x and x, not x and x plus h. And so their h value is 0, and you have this line that we call a tangent line. Instead of going through the graph at 2 different points, it touches the graph at 1 point, and it approximates a slope at exactly that point. So that's the instantaneous rate of change. And what happens is that we have the difference quotient, but my h is in the denominator. And we notice that h is now 0. And you can't have 0 in the denominator. So then we ask ourselves, how do we make this work? Well, instead of finding this and plugging in h equals 0, what we do is we find the limit as h approaches 0. We say, what would that be? What is that slope getting close to? And so if we're trying to find the slope of that tangent line, then we find that instantaneous rate of change. Another word for what we're doing is finding the derivative. So notice that finding the derivative of the function is the exact same thing. Right over here. We're finding the limit as h approaches 0 of the difference quotient. And we rewrite it by saying f prime of x. And f prime of x is the same thing as the slope of the tangent line. It's the same thing as saying the instantaneous rate of change. It's also the same thing as saying the derivative. And so we have all these different words that we're using to find the same thing. And if I find the derivative, then I can find the slope of the tangent line. And I find the instantaneous rate of change. So we're going to be finding the limit of the difference quotient as h approaches 0 all throughout this section. Let's get started. So the first example says, for f of x is equal to x squared, find f prime of x. Now saying f prime of x is the same thing as finding the limit of the difference quotient. So the first thing we have to do is plug in x plus h into x squared. And then we want to simplify that difference quotient. And you want to then simplify the numerator, whatever terms cancel out when you add them. And then you want to simplify it so that you factor out the h's. And then you want to reduce the fraction. And then recall that if you're finding the limit of a polynomial, you can just plug the value in. So as h approaches 0, this is going to go towards 2x plus 0, which is just 2x. And so f prime of x is the same thing as saying 2x. Now that I've simplified f prime of x, it's easy to plug in individual values of x. So f prime of 1 is just 2 times 1, and f prime of 2 is just 2 times 2. So we found f prime of x, f prime of 1, and f prime of 2. Alright? Looking at my work, you can see that as you write the limit of the difference quotient, I took the time each and every step of the way to write down the full equation, to write equals the limit of the function as h goes to 0. The limit of this function as h goes to 0. The limit of this function as h goes to 0. You can't skip steps, and you have to make sure that your formatting looks exactly like mine on your paper. Double check that before you move on. Thank you. Alright, for our second example, it's going to be the same as our first. They're asking us to find f prime of x, and to do that we want to find the limit of the difference quotient. So let's plug x plus h into our function. And for something like this, where we plugged x plus h into our cubic function, I would suggest doing that work somewhere on the side so you don't have to write this whole notation over and over again as you're simplifying that. So you can see that was a lot of steps here, and we have it simplified down to this step. So I'm going to take that and write it into my difference function. And so far I've written only x plus h cubed. I have to minus x cubed, and then I have to put this whole thing over h. And then let's simplify by adding or subtracting items in the numerator. So the x cubed and the minus x cubed will cancel out. And now you should only have h terms left in your numerator, and so let's factor out 1h. And now that I factored out 1h, I can reduce factors in the fraction. And then now that I have a polynomial function, as we find the limit, we can just plug in the values of h. So that would be 3x squared plus 0 plus 0. And so here is f prime of x. I'm going to erase all of my side work just to make room. So f prime of x is 3x squared. Keep in mind that my original function is x cubed, and my derivative is 3x squared. F prime of negative 1, I'll just take negative 1 and plug it in, and we end up at 3. This means that the derivative of f at negative 1 is 3. It also means the slope of the function at negative 1 is 3. It means the instantaneous rate of change is 3. And then f prime of 1.5 is 3 times 1.5 squared. That becomes 3 times 2.25, which is 6.75. This means that the slope of the function f at x equals 1.5 is 6.75. The derivative of the function is 6.75 at x equals 1.5. If this were a test question, I would give you some points just for the correct notation all the way down, for writing the limit as h approaches 0 of this function, for simplifying each step of the way. You would also get points for writing f prime of x is equal to as your final answer, and to solve f prime of negative 1 and f prime of 1.5. Look how I have all my equal signs lined up. Notice how my work is done vertically. Over here my equal signs are lined up. I have each line written, and I've given myself space to simplify, and I don't have stuff all mushed in together, right? So you want to look at this formatting. You want your page to look just like this. We have a quick check just to make sure that we remember the rules of limits and how can we calculate limits, and if we can remember the derivatives that we just found out. If we go off the regular definition of the derivative, we know that we're just finding the limit of the difference quotient. But we already found the limit of the difference quotient. Can we just add our results together? Yes, because that's one of the limit rules, is the ability to add limits. If we find the limit of f and the limit of g, then we can find the limit of f plus g. So since we already found the limit of each of these functions in the difference quotient, we can just say it is 3x squared plus 2x. We know that the derivative of this function is going to be the sum of the derivatives of each of those individual functions. And so there we go. Finding f prime of negative 2 is as simple as plugging this in. So f prime of negative 2 is 8, and f prime of 4 is 56. If you can remember that we can add up different parts of the derivatives, this makes our life easier. We didn't have to do the whole difference quotient all over again. We just were able to find out the derivative by adding up the parts and then applying that to our two answers. We're given a new function that we want to find the derivative of. Let's go ahead and write the steps out. F prime of x is going to be the limit of the difference quotient. And then let's go ahead and put in our specific function into this. And now we have something with multiple terms, so you have to be careful, make sure you distribute everything properly. That becomes 5x plus 5h plus 7, and then this minus turns into minus 5x minus 7. The whole thing over h. And then you want to add or subtract parts of the numerator to cancel out. So I get 5x minus 5x and positive 7 minus 7. So I'm left with just 5h over h. So I'll cancel out those h's. So now we just have the limit as h approaches 0 of 5. And that's a constant. There's no variable h in there. So when we try to evaluate this, we just get 5. Let's write that one time. F prime of x is equal to 5. So now if I'm trying to find f prime of 4, there's nowhere to plug in my 4. There's no x. There's nothing to do. So I just get 5. That's my constant function. This means that everywhere my slope is 5. Not just at 4, but everywhere. You have a constant slope of 5. That makes sense when we think about this function. It's a linear function, so of course its slope is 5. We see that slope right there. But now we're able to see that after we found the derivative. For video example 4, we're asked to find the derivative of the function 3 over x. And if you recall, we actually found the difference quotient of this function in a previous section, but we'll do it again. So the first thing we do is write down the definition of our derivative, and then let's plug it in with our actual function. And we get this function that has fractions within fractions, so let's multiply by the LCD of those inner fractions. So that cancels out with some of those denominators in the smaller numerators. And then we have this, and so let's just distribute that negative 3. Looking at this, you have to make sure you distribute that negative as well, so it becomes negative 3h. And then the 3x adds with a negative 3x to cancel out. And then I can reduce that h and that h, one in the numerator, one in the denominator, because they are factors. Keep in mind that this is a rational function, so to find the limit, we can just plug in h equals 0 and see what we get. And since that h goes to 0, we get negative 3 over x squared. So our derivative of 3 over x becomes negative 3 over x squared. Let's use that to find f prime of 2. F prime of 2 would be negative 3 over 2 squared. In other words, negative 3/4. And then we're asked to find an equation of the line tangent to the graph at x equals 2. So we actually know several things, and we actually have to do one more thing to figure this out. We know the slope, and we know the x value of the point. How do I find the y value of the point? By plugging this x value into our original function. Our original function was 3 over x. So f of 2 is 3 over 2. That means we have the point, 2, 3/2, and we have the slope, negative 3/4. Let's take that and make an equation out of it. That would be y minus 3/2 is equal to negative 3/4 times x minus 2. Let's simplify that. That becomes y minus 3/2 is equal to negative 3/4 x plus 3/2. And let's add 3/2 to both sides. That would give me 6/2 or 3. And so there we go. We have our equation in point slope form originally, then we solved for it in slope intercept form. And so there's our final answer. For all the examples so far, we found the limit of the difference quotient to find the derivative. Does that mean that we can find the derivative of every function? Or in other words, does that mean that every function is differentiable? Well, in order for some function to be differentiable, it needs to be smooth and continuous. If it is not continuous, we call it discontinuous, then it is not differentiable at that point. If it is continuous, but it's not smooth, then it's also not differentiable. Some examples of not smooth functions are functions that look like they have a corner. For example, the corner right here, the corner right here, or the two corners right here. This function can have derivatives at other places, but it does not have a derivative at the points that have been highlighted. It's not differentiable at these specific points. It might be differentiable other places because it is smooth and continuous on this part of the curve and smooth and continuous on that part of the curve. It's just at this one point that is not smooth and continuous. Therefore, it's not differentiable specifically at that one point. Additionally, a function is not differentiable if there's a vertical tangent. So as we see over here, when the slope goes vertical, we call it not differentiable. This last question just asks us, where is a function, the absolute value of x minus 6, not differentiable? Well, we want to make sure that it's smooth and continuous, that it does not have any gaps, and it does not have any corners. But if you're familiar with a graph of absolute values, you know that there's a corner somewhere. And this graph, x minus 6 in the absolute value, is shifted over on our x-axis. Let's graph it real quick. Here's a sketch of the graph. And we see that it has a corner right here. And so f of x is not differentiable at x equals 6. And the reason is it's not smooth at x equals 6. And notice that we're only giving the x value. We don't care about the y value right now. When we ask where does something happen, it happens at the x value. It is differentiable in other locations, but at x equals 6, because it has the corner, f of x is not differentiable specifically at x equals 6. And let's just summarize some of the things that we learned this section. The tangent line is a line that touches the curve at a single point, and that point is called the point of tangency. And so the secant line that we learned about last time crosses the curve in 2 points, but the tangent line touches at 1 point. The derivative of a function is given by f prime of x, written that way, and it's the limit of the difference quotient as h approaches 0. And that derivative is the same thing as finding the slope of the line tangent to the graph. It's the same thing as the derivative, and it's also the instantaneous rate of change. All three of those things mean the same thing. So as we're solving for it, they could ask any of those questions, you would do the same work. And then if you want to find the equation of the tangent line is given by this function, which is y minus y1 is equal to m times x minus x1. And so you have all of these pieces here. You need to practice them because this is really the crux of what calculus is. So thank you, have a good night, and get lots of practice. Bye!